Jason, if you can hear me, please let me know. I just want to check the audio. Jason, once again, Jason, if you can hear me and are viewing, please send me a text. I just want to make sure the audio is working. Oh, why, thank you, Aaron. Yes, Aaron. Just wrapping up. Found my pen. We'll start in just a moment. Good afternoon, everybody. I'm so glad you could join us. Today, I'm going to be doing a lesson about engineering and the AOL and Webelos engineering adventure. This was brought about because of the global pandemic, and I wanted to share my passion about engineering with all of you. So there's 4 requirements to the adventure. Only the first 2 are required. The number 3 and 4 are both optional. So we aren't going to do those today, but they're related to number 1 and 2 in such a way that if you just do a little extra, you can get numbers 3 and 4, though they aren't required. So let's start off with talking about what is engineering. And when I think about engineering, there is one word that comes to mind. Other people, I haven't seen this anywhere else, but the one word that comes to mind when I think about engineering is how. I don't think you can read that. It's how. How can we do something better? How can we build something? How do we make the world a better place? How do we create something new? How do we fix this problem? How do we do this? How do we solve that? How. How is the word that describes engineering best. Engineering is a problem-solving profession. We solve problems for a living. And there's a saying that I read about engineering that says, without engineering, science is just a philosophy. Engineers make science a reality. So, the way we think, too, as engineers, it's a special way of thinking that's a little particular to engineers and some other people as well, of course, that makes us excellent candidates for other fields throughout the world. So now we're going to jump straight into requirement number 1, different types of engineers. So the first type I'd like to talk about today is chemical engineering. And before we start, I have a little demo. I have here a little dish. It's got some vinegar and some salt in it, and I have some pennies. Old pennies, old pennies. So these pennies aren't shiny. This penny is shiny. Hold on, I'll get up close. So this penny is really shiny, right? Whereas some of these other pennies, they're kind of dull and brown and terrible, and they don't look very pretty. So what we can do through the power of a little chemical engineering is we can take these dull pennies and make them shiny. So I'm going to take some dull pennies. I'm going to put them in this vinegar solution. I'll keep some so that we can use them as reference. We take our dull pennies, we sit them in the vinegar. I can take my spoon, stir them around a little bit, and now we have a reaction, a chemical reaction. We'll let that sit for about 5 minutes. So what we can do is explain chemical engineering. So you might think chemical engineering and chemistry are the same thing, and I did too, but I did a little research. Chemists, they'll create the process. They'll find the chemicals and the things that work together to create something, and the chemical engineer will take that process and those chemicals and how it works and make it bigger and upscale it and give it a purpose or a use. So chemical engineers will use chemical processes to create, design, and refine objects, like what we're doing here with our pennies. We're making them shiny. We're refining them so they look brand new. So the chemical engineering world uses a lot of stuff from the periodic table. You'll learn more about it in 7th grade, but essentially, the entire world, if you break down objects, is made of elements. So the air that we breathe isn't just oxygen. It's a mixture. It's like trail mix, or it's like pasta with meatballs, or it's your cereal in the morning. Like Lucky Charms, you have your cereal and you have your marshmallows. They're mixed together. The air we breathe is the exact same way. The air is made out of oxygen, nitrogen, and a bunch of other gases that we can't see or smell, and of course, some other things like carbon and whatnot. So some sub-disciplines of chemical engineering, this is just the main branch, includes materials engineering, process engineering, and corrosion engineering, which relates back to our pennies. So our pennies, they aren't perfect yet, but one of them looks to be about good. So let me just pull that out and I'll dry it off. And then I'll bring it up to the camera. So this is the penny that we had just cleaned. I don't know how well you can see this, but this is the penny that we just cleaned right here. It's bright and shiny, and then this penny over here is just brown and dirty. It's exactly how the first one was when we put it in the vinegar. So, and you can do this experiment yourself right at home. You just take some dirty pennies, put them in vinegar and a little salt, mix it around, and it will clean the pennies. Now, this isn't just vinegar anymore. There's a little copper, because the copper from the pennies has dissolved into the vinegar. That's what the reaction is. And we can take that copper and put it on something else. That's what chemical engineers do. So now I want to move on to our second type of engineering, civil engineering, like architecture, but not quite. There's a difference between architects and civil engineers. The architects want to make things look good. They design the buildings, whereas the civil engineer figures out how to actually build it. The perfect building in a civil engineer's mind is plain gray concrete with no windows, because it's simple and it's easy to build and there's not a lot of work involved. That doesn't look good. That's why we have architects. So the two of them work together to build our world as we know it. They build bridges and dams and airports and sewers and roads and everything we need. Civil engineering also happens to be the oldest type of engineering that we have. All the way back in Roman times, they built the aqueducts and they built the roads that are still here 2,000 years later. They were some good civil engineers. But even before that, the Great Pyramids of Giza are thought to be considered the first example of civil engineering we have today. Subdisciplines of civil engineering. So civil engineering is the main tent, and inside of it, you can also have environmental engineering, where they protect the environment, structural engineering, and mining engineering, where they go mine in the ground for new ores and minerals. Our third main type is electrical engineering. It's like an electrician, but not quite. See the pattern? An electrician installs the wiring, whereas the engineer designs the wiring. They create things, like cell phones. I have another object to show you. So, last year, for our marching band show at the high school, I had to build 132, I believe, phones. It's a block of acrylic that I sanded on the outside, and it glows. And right here, this thing that makes it glow is a tiny little insert. I'll show it to you. So right up here, I have a battery, I have a switch, and then I have an LED light strip right on the top edge of this block. And then when you click the button, it turns on, it glows, and you can see it across a football field, even with the lights on. So this little insert with the lights is a good example of electrical engineering. But they don't have to only use electricity. They can also use magnets. Magnets make electric fields. Have you ever heard of an electromagnet? Or what you do is rub a magnet on a nail, an iron nail, and then that nail becomes a magnet. That's part of electrical engineering. So if that fascinates you, look into some electrical stuff. Electrical engineers also do electronics engineering, computer engineering, and power engineering. And I have one more thing. Right here, I have an old motherboard for a computer. This is something that an electrical engineer or someone in a subcategory of electrical engineer, like a computer engineer or an electronics engineer, they would design. They would put all the circuits on here right where they wanted them. They would use their knowledge to create this design, and then they would use this as a product for the world, to make the world a better place. That's what engineering is all about. So our final category, and my personal favorite, mechanical engineering. So, it sounds a lot like a mechanic. Mechanics and mechanical engineers are completely different. Don't ask a mechanical engineer to fix your car. Chances are they might not know how. That's when you go to your mechanic. The mechanic assembles things and fixes them. The mechanical engineer builds and designs those things. So an engineer designed the engine in your car, whereas a mechanic will fix the engine in your car. To put it simply, A mechanical engineer designs moving things and hot things. So like engines. Engines are a great example. Or air conditioning systems, heating systems, and anything else that deals with heat transfer or thermal energy. They can also build the biggest things, like spaceships. There's a lot of engineering that goes into a spaceship from all 4 categories of engineering we're talking about today. It's also the biggest and broadest category. There are a lot of subcategories underneath mechanical engineering that go into it, such as manufacturing engineering, acoustic engineering, they deal with sound and how sound is produced and recorded, and thermal engineering, which I went over, they do like air conditioning systems and hot engines and how to reduce heat or use that heat for the benefit of all of us. There are also some categories that are a mix of both, like aerospace engineering, they do a lot of spaceships, nuclear engineering, they build the nuclear power plants, railway engineers, they do a lot with magnets. They're trying to make maglev trains, literally trains that float above the ground. Mechatronics, it's an almost 50-50 split between mechanical and electrical smushed together. Software engineering, and so many others. There are over 40 different types of engineers out there and engineering disciplines. So now we're going to jump down to requirement 2. This one says it's very mechanical based. We have to examine a set of blueprints or specifications, and then using them as a model, we have to prepare our own set of blueprints to design a project. So I have a set of blueprints. Now you may ask why blueprints are called blueprints. Well, an easy answer would be they're blue, or they used to be blue. It's a process of how they were made. Back in the 1870s, I believe, it was very hard to copy documents. You had to stick it on a press, or scan it, or just draw a new one by hand. So the engineers came up with a way where you can copy it using chemicals, and that process is what made blueprints blue. Well, this is not planned. Anyway, I'll just use this first one, and I'll come up real close. So this blueprint is an example of a clock that I designed and built last year. Did it work? Well, it kind of worked. So let's talk about this. This is our main original drawing. So there's my clock. That's what it looked like. In the end, it didn't work. I broke a piece and never bothered to go fix it. I should really do that. And then we have, on the other side, we have some drawings and dimensions. And then in the bottom right corner is the most important part. This is called the title block. So you'll see this number. This was my ID number because I took this to a competition. So normally this would be your name. So there's a couple important pieces to keep in your title block. The first one being, what is this? So this drawing is the main assembly of my clock. I have some other drawings, and I can show those to you, of the individual parts that go into creating this. We have who drew it. So this would be me. That's my ID number for the competition. We have what it's a part of. So this is all for a skeleton clock. It's a special type of clock. And then we have a scale. We have how many sheets there are. We have the paper size. And then I did leave a few things out. because again, I took this to a competition and they had their own special set of rules. But in general, you're also going to want to include what is this made of, the material, and when it was drawn, so that someone can look at two copies of the exact same thing and figure out which one is most recent, because you have the date on there. So allow me a moment, and I will pull up another one that shows a better example of the next part. So right here we have, and I rolled up the rest of it because it likes to curl. We have a rather ugly looking drawing. This is probably the worst example I could have chosen, but it'll work. So we have the clock face. This is the main body of the clock, and there's dimensions just scattered all over the place. So hold on, this really wasn't the best design. Okay, this one should be, yes, this one should be better. So this is the escapement wheel. This is what actually makes a clock a clock. And there's a few important parts. We see a picture of what it looks like. We have all the relevant lines and information that someone needs to recreate this object, whether on paper or as like an actual gear. And then we have dimensions. Dimensions are especially important because someone needs to know how big it is. So our outside diameter, the largest circle we have, is 4 inches. And then the inside, on the inside of all of these teeth, is 3 inches. So this makes both parts of a drawing complete. You have a title block to explain what the drawing is, and then you have the drawing itself, which has the views of the object, and it has dimensions so people know how big it actually is. So now I'm going to give a short walkthrough about what you can build for a project and how you would go about doing it. So the requirement says you need to start off with a blueprint. So let's make a blueprint. Let's make a drawing like one of the ones I just showed. And it's for a project that we're going to build. So now we have to think about a project that we want to make. I like launching things. So I'm going to draw a catapult. So here we go. So let's start off with a base of catapult. And we're only going to draw it from one view, and I'll show you this in a moment. So we'll have a base of our catapult. We'll have a front post that the rubber bands can sit off of. Of course, we're going to be bending it, so we'll need some braces. I'll have to add in our spoon, how we're launching the object, right? So here's our spoon. I'm going to build it out of cardboard and a spoon. We'll have a rubber band in here too, so that we can actually draw it back. And that looks pretty good for a front view. So let me show that to you. So right here with my catapult, we have a base plate on the bottom. That's what sits on the ground. We have a front post. We have a brace so that it is more stable and sturdy. We have our spoon, and we have a rubber band. But it's not complete. I'm missing some things. Number one, I'm missing dimensions, and number two, I don't know how wide this is. You can see it from the side, but how thick is it? Is it like 2 inches farther into the paper? Is it 6 inches farther into the paper? So we need another view. So this time we'll draw it from a different side. So we'll say here is one of my bottom bars. Here is another one of them. So if I drew this from the side, I'm going to draw two versions, or I'm going to draw it in a different plane, like it's 3D. So here's a front post. Here's another front post. We'll draw my spoon, because I have a spoon in here. And then we'll draw, we can't see the rubber band from the view that I'm drawing it in, so I won't draw the rubber band. But I need something to connect. Ooh, I'll draw the braces too, because we can see those. And then we need something to connect the two sides of the frame together. Otherwise, they'll just fall apart. So I'll throw in a brace at the bottom, and I'll throw in a base at the top, so our catapult can actually launch things, right? Because when the spoon comes up and it slams into the bar, it's got to throw an the spoon has to stop for the object to keep going. So here's what I've done. I've taken our original drawing and I have changed it. I'm looking at it from this way, right? Not from the face, but from the side. So when I do that, we get something that looks like this. So here's our frame with a brace and a bottom plate and a front post, and then here's our spoon in the middle, and then here is our other plate, and then I have braces that go back and forth in between. And we can't see the rubber band because it's hidden behind the spoon. But once again, I don't know how big it is. This could be like the size of a golf ball. This could be the size of a basketball. It could be the size of a house. Who knows? So that's what's next. So now I'm going to dimensions. So let's say it is about 6 inches long. We'll make it kind of small. And then 5 inches tall. 5 inches tall sounds about right. It looks proportional. 5 inches tall. And then how wide is it? Ooh, I don't know. We'll go another 5 inches. We'll call it square. So here we go. I've told you that our catapult is now 6 inches long by 5 inches tall and 5 inches wide. So this looks like a good engineering drawing. I mean, it's not perfect and it could be better, but I'm doing it by hand. But there's still something missing. I don't know what this is. I don't know who drew it or when it was drawn. So what we're going to do is fix that. I'm going to throw on a title block. It's the other part of an engineering drawing. And I haven't exactly left myself space in the bottom right corner, but I can make it fit. So we need to know what it is. It's a catapult. And then we need to know who drew it so that we can ask them if we have questions. We need to know when it was drawn so that if we have questions about the version, we know how recent this was or if there have been any updates. We need to know what it's made out of. And I have a lot of cardboard, so I'm going to make it out of cardboard. And for the purposes of what we're using it for, that is all we need. So let me show you my title block. We have, in the bottom right corner in our title block, we have what it is. It's a catapult, who drew it, when it was drawn, and what it's made out of. So now, to fulfill requirement number 2, we have to use this blueprint and go build our object. And you could do anything. It doesn't have to be a catapult. You could build a cannon. You could build something with pulleys. You could build anything you want. But being the prepared Eagle Scout that I am, I've already built this catapult. So, here it is. Boom, catapult. My dimensions were a bit off, but it is a catapult. It has the spoon, it has a rubber band, it has a brace on the bottom. Two, actually. I missed that on my drawing. It has braces on the sides, and it is effectively a catapult. You can put objects in the spoon, pull them back, and fire them. However, if you just notice, the spoon, it came out. I have a little slot in here. That's how I solved that engineering problem, because without this bar at the bottom, the spoon would just fly everywhere. It wouldn't work. But when I pull it back and I let go, it flies out of that spot. That's still an engineering problem, but I didn't solve it. I'm going to let you guys solve it if you choose to build a catapult. And that's all. You have learned about the different types of engineering. We went over what you need to have on a blueprint or a drawing. We did a drawing, and then I built a project, and I shared it with all of you. So now that's what you have to do for the project. Requirement 3 is to explore other fields. I explained all 4 instead of just 1. You only need to learn 1 if you want to go for all 4. That would satisfy requirement number 3. And then you can also build more projects. And if you build 2 more projects, that qualifies as requirement number 4. So you only have to do requirements 1 and 2, which we just went over. And then if you go above and beyond, you can do like twice that if you're really interested. And then you can get requirements 3 and 4. And then you have the adventure. So I'd like to thank all of you for coming out today, learning about engineering with me. And that's it. That's the end of class. I'm going to stick around. If you have any questions, you can type them in the chat. I should be able to see them, and I will answer those questions for you. Thank you all very much. If you build your project, feel free to tag the Scout Reservation on the post. I'd love to see what you guys built. You can be extremely creative, and there's tons of projects on the internet that you can take, adapt, and then use to learn about engineering. Thank you all. I'll stick around for questions if anyone has any. Oh no. Hope, I'm sorry I didn't get to the point. I hope I addressed it eventually. I had to explain what everything was. Where are some Graham, excellent question. Graham wants to know, what are some places mechanical engineers work? So mechanical engineers can go work anywhere. So you've probably heard on the news or somewhere else that NASA is putting people back on the moon. One of the well-known places would be NASA. Another place would be SpaceX, run by Elon Musk. They do a lot of things with mechanical engineering. You can work in factories designing parts and machinery. You can work in workshops, building small little parts. That's where I'm trying to go. You can go build stages. You can build cars. You can build furniture and sinks and machines. And another place a lot of mechanical engineers will go to work is somewhere with heating, ventilation, or air conditioning systems, because we get all of that information in the college and in our education. So I hope that answered your question. If anyone else has anything, please let me know. I do love answering questions. And I myself, if I didn't say it, I am studying to be a mechanical engineer right now. And I wanted to share that passion with all of you. So that's why I'm doing this adventure. Thank you, Jason. Thank you very much. I did my best. I actually forgot something too, so I'll pull it out right now. Woo! Oh no, that's not good. I'll have to fix that. So here I have a cuckoo clock, right? And this, I'm fascinated by clocks, if you can't tell. So if we pop open the back of our cuckoo clock, and this is very mechanical engineering stuff, we can see on the inside. I don't know if you guys can see that really well, but all of that gearing, all the mechanisms in there, how it operates, the chains, and how it all links together. That is mechanical engineering at its finest right there, and I love that. So yes, we have another question from Graham. So what school subjects help with engineering? And the truth is, all of them. But of course, you want me to get into specifics, so I'll address them. There's a lot of science and there's a lot of math. So you might be wondering what math is for, like why you need to know science. It's so that you can find an interest in something like engineering, and you can develop your math and your science skills further, and you can go do that. Now, English is also very important. Engineers are useless if they can't tell other people effectively about what they've done. That's why we use drawings, and a lot of times there's some written reports. So good English is important. History as well is important because we can learn from the engineers of the past to improve what we do in the future. So English and history are important, but they're not primary. Math and science are very important in engineering. I use a lot of math and a lot of physics, which is basically just applied math. There's just a lot of math. And as I just thought of it, one more question from Graham. Graham wants to know, what are some things that you will do as a mechanical engineer once you have that job? Ooh, that's tricky. So I've never been a huge fan of the thermal side of mechanical engineering. So if I have a really hot piece of iron and I spray some water on it and it gets cold, how that affects the properties. That's very material science kind of stuff. And like how heat flows, through houses. I've never been too interested in that, but I do love like mechanical machines and clocks especially. I love clocks because you can see all the gears, and the gears mesh together and they move. And if I just had like a huge wall in my house of gears, that would be fantastic. But right now, one of my dreams is to go work at NASA and help put people on Mars. That's one of my dreams. So when I graduate as a mechanical engineer, I'll try and get a job at NASA or at SpaceX, something related to space. But, of course, I've also gotten into the technical side of things, and like stage crew work and lighting. I'm going to try and get a job with and travel the country and the world with them, help on productions, and maybe doing some mechanical engineering for them and have some fun. And then I'll settle down later on and I'll try and go work on, rocket ships and fast cars and maybe some airplanes and do some really cool stuff. That's what I want to do. So with that, once again, I want to thank all of you for coming out, supporting. Stay safe during the pandemic, and if we meet sometime in the future, we can talk about engineering all day long. And if you come to camp this summer, I'm sure we'll have some cool stuff that you can play around with in the STEM Lodge. Graham says thank you. Thank you, Graham. I hope we meet up at some point and we can talk about engineering and I can tell you about all the cool things I've done and the trebuchets I've built and the cannons I'm thinking about and all the projects rattling around in my head. So once again, thank you all. If you have any other questions, leave them in the comment section and I can address them in the future. And then stay safe. And then if you build a project, tag us. I would love to take a look at it and see what you guys have done. Thank you all very much.